This is a continuation of Part 1. Part 2. The silence from Proxima b and Alpha Centauri. The absence of any detectable signals despite decades of listening demands explanation. Either intelligence is rare, or it is quiet, or it is absent from our immediate neighborhood for reasons we have not yet understood. Each possibility carries profound implications. This question, formalized as the Fermi paradox, after physicist Enrico Fermi's famous lunchtime query in 1950, provides a framework for thinking about what the study of Proxima b reveals not just about planetary science, but about the nature and prevalence of life and intelligence in the cosmos. Let us examine how the detailed understanding of M-dwarf planetary systems reshapes our approach to this enduring puzzle. The classical Fermi paradox assumes that habitable planets are common, that life arises readily, that intelligence evolves frequently, and that technological civilizations expand or at least communicate across interstellar distances. Given these assumptions, the galaxy should be teeming with evidence of extraterrestrial intelligence. The absence of such evidence, the great silence, demands that at least one assumption be wrong. The study of M-dwarf systems challenges the first assumption directly. If planets around red dwarfs struggle to maintain habitable conditions, then the number of genuinely habitable planets in the galaxy might be far smaller than optimistic estimates suggest. The habitable zone around M-dwarfs exists, but occupying that zone provides no guarantee of habitability. Stellar activity, atmospheric stripping, tidal locking, and photochemical instability create barriers that might prevent most M-dwarf planets from supporting life. This realization shifts the statistical landscape. Red dwarfs constitute roughly 70% of all stars. If their planets are largely uninhabitable, then 70% of the galaxy's stellar real estate effectively drops out of consideration for hosting life. The remaining 30%, Sun-like G dwarfs, K dwarfs, and a fraction of quieter M dwarfs, must carry the entire burden of cosmic biology. But here's where the numbers become interesting. Even with this reduction, the galaxy contains hundreds of billions of stars. If only 1% host habitable planets, that still implies billions of potentially life-bearing worlds. The Fermi paradox persists even under pessimistic assumptions about M-dwarf habitability, because the galaxy is simply so vast. However, the analysis cannot stop at raw numbers. The distribution of habitable planets matters as much as their total count. If habitable worlds cluster around certain stellar types in certain galactic regions or at certain epochs of cosmic history, then the pattern of life in the universe becomes structured rather than uniform. Understanding that structure helps explain why we might find ourselves in a neighborhood devoid of other intelligences, despite a galaxy potentially rich with life elsewhere. And this is where Proxima b's story intersects with galactic archaeology. The Milky Way has a history spanning over 13 billion years. Stars have formed, lived, and died through countless generations. The heavy elements that constitute rocky planets and living organisms were forged in stellar cores and supernova explosions, accumulating in the interstellar medium over cosmic time. Early in the galaxy's history, heavy element abundances were low, limiting the formation of Earth-like planets. Only as generations of stars enriched the galaxy with metals did conditions become favorable for rocky planet formation. The Sun and Solar System formed roughly 4.5 billion years ago, when the galaxy had already existed for over 9 billion years. By that time, heavy element abundances had reached levels comparable to today's. Earth-like planet formation was possible and clearly occurred at least once. But what about earlier epochs? Could habitable planets have formed around stars born 6, 8, or 10 billion years ago? The answer depends on metallicity thresholds for planet formation. Studies of exoplanet host stars reveal correlations between stellar metallicity and planet occurrence rates, at least for giant planets. The relationship for small rocky planets is less clear, with some evidence suggesting that rocky planets form across a wide range of metallicities. If true, habitable planets might have existed in the galaxy long before Earth formed, giving life elsewhere a head start measured in billions of years. This temporal dimension adds complexity to the Fermi paradox. If habitable planets existed billions of years before Earth, any life arising on them had vastly more time to develop intelligence and technology. A civilization with even a million-year head start, let alone a billion, should have had ample opportunity to explore or colonize the entire galaxy. The timescales for interstellar expansion, even at modest fractions of light speed, are measured in millions of years, negligible compared to the galaxy's age. Yet we see no evidence of such expansion. No megastructures orbiting nearby stars, no self-replicating probes in our solar system, no signals from ancient civilizations. The silence persists across all wavelengths and all detection methods we have tried. One resolution to this puzzle invokes the concept of great filters, hypothetical barriers that prevent life from progressing through certain stages of development. A great filter might operate at any point. The origin of life from non-living chemistry, the evolution of complex cells, the development of multicellular organisms, the emergence of intelligence, the transition to technological civilization, or the long-term survival of such civilizations. If any of these transitions is sufficiently improbable, it could explain why the galaxy appears empty, despite conditions favorable for life. The study of M-dwarf planets suggests where some filters might operate. The hostile environments around red dwarfs, the atmospheric stripping and radiation bombardment, might prevent life from establishing itself at all. Even if simple chemistry produces organic molecules, the continuous assault from stellar activity might prevent those molecules from organizing into self-replicating systems. The origin of life itself might fail under such conditions, constituting a filter at the earliest possible stage. Alternatively, life might arise but fail to persist. The episodic superflares that characterize active M-dwarfs could periodically sterilize planetary surfaces, resetting any progress toward complexity. Life might establish itself during quiet intervals, begin evolving, and then be wiped out by the next major flare event. Over billions of years, this cycle of origin and extinction might prevent the accumulation of evolutionary progress needed for intelligence to emerge. And this detail suggests something unsettling about Proxima b specifically. The planet has orbited its star for nearly 5 billion years, comparable to Earth's age. If life ever arose there, it has had ample time to evolve complexity. But if Proxima Centauri's activity has repeatedly sterilized the planet, that time might have been fragmented into countless short intervals separated by extinction events. 4.5 billion years of opportunity, but no single stretch long enough for complex evolution to unfold. The concept of windows of habitability captures this possibility. A planet might be habitable only during certain periods of its history, when stellar activity happens to be low, when orbital conditions happen to favor stability, when atmospheric composition happens to permit clement surface conditions. If these windows are short compared to the timescales needed for life to evolve intelligence, then even genuinely habitable planets might never produce technological civilizations. For Earth, the window has been remarkably long. The Sun is a relatively stable star, with activity cycles that modulate but never threaten global habitability. Earth's magnetic field has protected the atmosphere for billions of years. Plate tectonics has regulated climate through carbon cycling. The combination of favorable circumstances has allowed an unbroken stretch of habitability spanning nearly 4 billion years, enough time for life to progress from simple cells to complex ecosystems to intelligence. If such unbroken stretches are rare, if most potentially habitable planets experience interrupted habitability that resets evolutionary clocks, then intelligence might be far rarer than simple life. The galaxy could be filled with worlds where microbial life repeatedly arises and is repeatedly destroyed, never accumulating the complexity needed for thought and technology. However, the deeper researchers examined this possibility, the more alternatives emerged. One alternative involves the role of subsurface environments in maintaining continuous habitability. If life retreats underground during surface sterilization events, it might survive even the most violent stellar outbursts. Subsurface oceans, shielded by kilometers of rock and ice, would be immune to stellar flares, coronal mass ejections, and atmospheric stripping. Life in such refugia could persist indefinitely, evolving slowly in stable conditions, regardless of surface chaos. This scenario suggests a galaxy filled with subsurface biospheres, hidden from remote detection, quietly evolving in the dark. Such life might never develop technology, lacking access to the energy and resources needed for industrial civilization. It might never produce signals we could detect or artifacts we could observe. The Fermi paradox might be resolved not by the absence of life, but by its confinement to inaccessible environments. For Proxima b, this possibility remains open. Even if the surface is sterile, even if the atmosphere has been stripped away, subsurface oceans might persist, warmed by residual internal heat or tidal dissipation. Life in those oceans would be invisible to telescopes, undetectable by any current technology. We would never know it exists without direct exploration, probes descending through ice shells to sample the waters beneath. But here's where the story takes yet another turn. The concept of subsurface habitability, while scientifically plausible, raises questions about what we mean by habitability in the context of the search for extraterrestrial intelligence. Habitability for microbes differs from habitability for complex life, which differs from habitability for technological civilizations. The factors that permit each level of biological complexity might be distinct, creating a hierarchy of habitable conditions that narrow progressively as we ascend the ladder of complexity. Proxima b might be habitable for subsurface microbes, while being completely uninhabitable for surface civilizations. The planet might host life without hosting minds. It might contribute to the galaxy's biological abundance without contributing to its intellectual community. This distinction matters for how we interpret the Great Silence. The absence of signals does not necessarily mean the absence of life. Only the absence of communicating intelligence And yet, even this nuanced picture might be too simple. Recent theoretical work has explored the possibility that intelligence arises through pathways very different from Earth's evolutionary history. On Earth, intelligence emerged from animal life, which emerged from eukaryotic cells, which emerged from prokaryotic ancestors. Each step requires specific conditions and considerable time. But other pathways might exist. Intelligence might arise in collective systems, like the distributed information processing of slime molds or ant colonies, scaled to planetary levels. It might emerge in chemical networks without cellular organization. It might develop in substrates we would not recognize as alive by terrestrial standards. If intelligence can arise through diverse pathways, then the conditions required might be broader than our Earth-centric perspective suggests. Planets inhospitable to Earth-like life might still produce intelligent systems through alternative routes. The Great Silence might reflect not the absence of intelligence, but our failure to recognize its alien manifestations. This possibility, speculative as it is, guards against the assumption that terrestrial biology provides a universal template. We have one example of intelligent life, ourselves, and that example emerged through a specific historical pathway on a specific planet around a specific type of star. Generalizing from a sample of one is statistically hazardous. The universe might contain forms of intelligence so different from ours that we would not recognize them, even if we encountered direct evidence. But speculation must be grounded by what we can actually observe and measure. Let us return to the concrete science and consider what ongoing and planned observations of the Alpha Centauri system might reveal about these larger questions. The search for technosignatures, evidence of technology rather than biology, represents a distinct approach to detecting extraterrestrial intelligence. Unlike biosignatures, which indicate the presence of life through chemical disequilibrium in atmospheres, technosignatures indicate the presence of technology through artifacts, emissions, or modifications that only intelligent beings would produce. The classic technosignature is a radio signal, the target of SETI searches since Frank Drake's Project Ozma in 1960. Radio waves travel across interstellar distances with minimal absorption, making them efficient for communication. A civilization wishing to announce its presence, or simply using radio for its own purposes, might produce signals detectable by our receivers. Decades of listening have detected no confirmed artificial signals, but the search has covered only a tiny fraction of the available parameter space. We have looked at limited frequencies, limited directions, and limited times. Absence of evidence, in this case, does not constitute strong evidence of absence. The breakthrough. Listen Initiative, the most comprehensive SETI program ever conducted, has observed Proxima Centauri extensively. In 2020, the program detected an intriguing narrowband signal at 982 MHz during observations of the star. Designated BLC-1, the signal exhibited characteristics consistent with a potential technosignature. It appeared to come from the direction of Proxima Centauri. It drifted in frequency as expected for a signal from an orbiting planet, and it was not obviously attributable to known terrestrial interference. The discovery triggered intense scrutiny and follow-up analysis. Ultimately, researchers concluded that BLC-1 was almost certainly terrestrial interference, likely from equipment operating near the Parkes radio telescope in Australia, where the observations were made. The signal's properties, while initially tantalizing, matched patterns expected from local sources better than from extraterrestrial origins. Another false alarm in the long history of SETI candidate signals. Yet the episode illustrates both the challenges and the potential of technosignature searches. The Alpha Centauri system, including Proxima Centauri and its planets, remains a prime target precisely because of its proximity. Any technological activity in that system would produce stronger signals at Earth than activity around more distant stars. If a civilization exists at Proxima b, even low-power transmissions might be detectable by current or near-future instruments. The absence of detected signals constrains the possibilities. Either no technological civilization exists in the Alpha Centauri system, or such a civilization exists but does not produce detectable radio emissions, or our searches have simply failed to observe at the right time and frequency. The parameter space remains large enough that the third possibility cannot be excluded, but continued non-detection gradually strengthens the case for the first or second options. Beyond radio, other technosignature searches target different types of evidence. Optical SETI looks for laser pulses, brief flashes of coherent light that would stand out against the continuous emission from stars. A civilization using lasers for communication or propulsion might produce such flashes, detectable by high-speed photometers monitoring nearby stars. Observations of Proxima Centauri have not detected any anomalous optical transients, though coverage remains incomplete. Infrared searches target waste heat, the thermodynamic consequence of any large-scale energy use. A civilization harnessing a significant fraction of its star's energy output, perhaps through a Dyson sphere or swarm of collectors, would produce excess infrared emission detectable as an anomaly in the star's spectrum. Surveys of nearby stars, including Proxima Centauri, have not identified any such anomalies, suggesting that if civilizations exist nearby, they have not undertaken mega-scale engineering projects or have done so in ways that minimize waste heat signatures. The null results across multiple search modalities paint a consistent picture. The Alpha Centauri system shows no evidence of technological activity. This does not prove such activity is absent, only that it is not detected at current sensitivity levels. But it does constrain the space of possibilities, ruling out certain types of technological civilizations while leaving others compatible with observations. And this is where the study of Proxima b intersects with broader questions about the nature and behavior of technological civilizations. If civilizations exist but remain undetected, they must either be rare, short-lived, non-technological, or deliberately quiet. Each possibility carries different implications for the future of humanity and for our expectations about the cosmos. Rare civilizations imply that the great filters operate strongly, preventing most potentially habitable planets from producing intelligence. The challenges facing M-dwarf planets, as exemplified by Proxima b, might constitute part of this filtering, eliminating a large fraction of the galaxy's real estate from consideration. Combined with filters at other stages, the origin of life, the evolution of complexity, the emergence of technology, the cumulative effect might reduce the expected number of civilizations to very small values. We might be one of a handful in the entire galaxy, or we might be entirely alone. Short-lived civilizations imply that technological societies tend to destroy themselves or collapse before becoming detectable across interstellar distances. Nuclear war, environmental catastrophe, resource depletion, or other existential risks might terminate civilizations before they can expand or communicate. If the average civilization lasts only a few centuries before extinction, the galaxy at any given moment would contain few contemporaneous civilizations, and the chances of temporal overlap would be small. Non-technological civilizations imply that intelligence does not inevitably lead to technology, at least not the kind of technology that produces detectable signatures. Intelligent beings might exist in oceanic environments without access to fire, or in gas giant atmospheres without solid surfaces for construction, or in social structures that do not prioritize technological development. Such civilizations would leave no radio signals, no megastructures, no artifacts in space. They would be invisible to our searches, while still contributing to the galaxy's inventory of mines. Deliberately, quiet civilizations imply that advanced societies choose not to broadcast their presence, perhaps out of caution, perhaps because they have transcended the need for expansion, perhaps because they observe a galactic norm of non-interference. This possibility, sometimes called the zoo hypothesis, suggests that we might be under observation without knowing it, studied by intelligences that choose to remain hidden. The absence of evidence would then reflect not the absence of civilizations, but their policy of concealment. Each of these possibilities remains compatible with current observations. We cannot distinguish between them based on null results alone. Only positive detection, finding evidence of life or technology elsewhere, would definitively resolve the question. Until then, the Fermi paradox persists as an open problem, a puzzle that Proxima b and similar studies inform but do not solve. However, the deeper consideration of these possibilities shapes how we plan future searches and how we interpret future results. If civilizations are rare, then finding even microbial life elsewhere would be enormously significant. It would suggest that the filters operate at stages beyond the origin of life, that life itself is not the bottleneck. The implications for humanity's future would be mixed. We would know that life arises readily, but we would also know that something prevents most life from reaching intelligence. The nature of that filter would become the crucial question. If civilizations are short-lived, then finding evidence of past civilizations, extinct technologies, or abandoned artifacts would be possible even in a galaxy currently devoid of active mines. The search for such relics, sometimes called SETA, search for extraterrestrial artifacts, represents a distinct research program from traditional SETI. Probes, structures, or debris from past civilizations might persist for millions or billions of years, outlasting their creators. The solar system itself might contain such artifacts, undetected in the vast volume of space we have not yet explored. If civilizations are deliberately quiet, then passive listening might never succeed. Active messaging, transmitting signals intended for potential receivers, might be necessary to initiate contact. This approach, sometimes called METI, messaging to extraterrestrial intelligence, remains controversial. Some researchers argue that revealing our presence to unknown civilizations poses existential risks. Others counter that any civilization capable of reaching us already knows we exist from our radio emissions over the past century. The debate remains unresolved, but it influences how we approach the search for intelligence in systems like Alpha Centauri. And this brings us to another dimension of Proxima b's significance, one that extends beyond the scientific into the realm of human aspiration and long-term planning. Proxima b is not just a scientific target. It is a destination, the nearest potentially habitable world beyond our solar system. Whatever its actual conditions turn out to be, it represents the first waypoint on any journey toward the stars. Understanding it, characterizing it, mapping its environment, these are prerequisites for any eventual interstellar mission, whether robotic or crewed. The breakthrough starshot concept, discussed earlier, targets Alpha Centauri precisely because of its proximity. A successful flyby mission would return images and data that transform Proxima b from a statistical inference into a known world. But Starshot is only the beginning. More ambitious missions might follow, larger probes with greater capabilities, eventually perhaps vehicles capable of orbital insertion rather than mere flyby. The engineering challenges are formidable, but they are challenges of technology, not physics. Nothing in the laws of nature prevents interstellar travel. It is merely very, very difficult. The planning horizon for such missions extends across generations. The scientists and engineers working on Starshot today will likely not live to see the mission arrive at its destination. The data returned will be analyzed by researchers not yet born. This multi-generational timescale requires institutions and commitments that transcend individual human lifetimes, a kind of civilizational project that humanity has rarely undertaken. Yet such projects are possible. The great cathedrals of medieval Europe took centuries to complete, with workers contributing to structures they would never see finished. Modern scientific infrastructure, from particle accelerators to space telescopes, often spans decades from conception to operation. Interstellar missions simply extend this timescale further, requiring commitments measured in centuries rather than decades. Proxima b provides a focus for such commitments, a specific target, a defined goal, a concrete objective around which resources and efforts can organize. Without such a focus, interstellar aspirations remain diffuse, abstract, easy to defer. With Proxima b as a destination, the project acquires tangibility, a sense that what is being attempted matters in a specific, addressable way. But here's where the scientific and aspirational threads interweave. The more we learn about Proxima b, the more we can assess whether it represents a worthy destination for human attention and resources. If the planet turns out to be completely sterile, stripped of atmosphere, baked by radiation, geologically dead, it might still warrant robotic exploration, but would represent a poor target for colonization or long-term human presence. If, on the other hand, observations reveal an atmosphere, surface water, or signs of geological activity, the planet becomes far more interesting as a potential future home. The question of colonization, even in the far future, connects to the broader issue of humanity's long-term survival and expansion. Earth will not remain habitable forever. The sun's luminosity increases over geological time, and within roughly 1 billion years, Earth's surface temperature will rise to levels incompatible with complex life. Long before that, other existential risks, from asteroid impacts to supervolcanic eruptions to self-inflicted catastrophes, threaten human civilization. Spreading beyond Earth, first to other bodies in the solar system, and eventually to other star systems, represents a hedge against extinction, a way to ensure that the human story continues, regardless of what happens to our home planet. Proxima b, as the nearest potentially habitable exoplanet, occupies a symbolic position in this vision of cosmic expansion. It is the first step, the initial proof of concept, the demonstration that interstellar settlement is possible. Even if centuries or millennia pass before humans actually reach it, the knowledge that such a destination exists shapes how we think about humanity's future trajectory. Yet we must balance aspiration with realism. Interstellar travel remains beyond current capabilities. The technical challenges are immense, the costs astronomical, the timescales daunting. Before committing resources to interstellar projects, humanity faces more immediate challenges: climate change, resource depletion, conflict, inequality. The argument for interstellar investment must contend with the argument for addressing pressing terrestrial problems. The two are not mutually exclusive, but resources are finite and priorities must be set. The scientific study of Proxima b informs this prioritization by clarifying what we might find if we ever arrive. A sterile, hostile world offers less motivation for enormous investment than a world with potential for habitability or even life. The more we learn from telescopes, the better we can assess the value of eventual missions. In this sense, remote observation and interstellar aspiration are not alternatives, but complements, each informing and motivating the other. And this leads to a deeper reflection on what the study of Proxima b reveals about the nature of scientific inquiry itself. Science proceeds through the interaction of theory and observation, each shaping the other in an iterative dance. We propose models of how planets form, how atmospheres evolve, how stars behave. We make predictions based on those models. We compare predictions to observations. When discrepancies arise, we revise the models, generating new predictions, seeking new observations. The cycle continues indefinitely, with understanding deepening asymptotically toward truth without ever fully reaching it. Proxima b exemplifies this process. Early models of habitable zone planets suggested relatively benign conditions. Observations revealed challenges: stellar activity, atmospheric loss, tidal locking, that required model revision. New models incorporated these challenges, making new predictions about atmospheric chemistry, surface conditions, and potential habitability. Future observations will test these predictions, leading to further revisions. The process has no endpoint, only progressive refinement. This iterative nature means that our current understanding is provisional, the best picture available given current data, but certain to be revised as new data arrives. Humility about our conclusions is appropriate. What we think we know about Proxima b today might look quite different in a decade, after the extremely large telescope has observed it, after JWST has accumulated more data, after theoretical models have incorporated new physics. The scientific enterprise is comfortable with this provisionality, understanding that tentative knowledge is better than no knowledge, and that revision is a feature, not a bug. Yet provisionality does not mean arbitrariness. The constraints tighten over time. The range of possibilities narrows. Each observation rules out certain scenarios while remaining compatible with others. The current picture of Proxima b, a world facing significant habitability challenges but not definitively ruled out as potentially life-bearing, is more constrained than the picture in 2016 when the planet was first announced. The picture in 2030 or 2040 will be more constrained still. This progressive constraining is what science accomplishes. Not final answers, but increasingly refined approximations. Not certainty, but ever better estimates of likelihood. The question of whether Proxima b harbors life might never receive a definitive yes or no answer, but the probability estimates will sharpen, the error bars will shrink, and the picture will clarify. And perhaps that is enough. Perhaps the value of studying Proxima b lies not in the answers it provides, but in the questions it forces us to ask. Questions about habitability and life. Questions about stellar physics and planetary evolution. Questions about the future of human exploration and the long-term trajectory of our species. Questions about our place in a cosmos that may or may not contain other minds, other seekers, other beings looking up at their night sky and wondering if anyone is looking back. The dark truth about Proxima b, in the end, is that there might be no simple truth at all, only complexity, contingency, and the slow accumulation of understanding through patient observation and careful reasoning. The beginning that we spoke of, the opening that the dark truth revealed, leads not to a destination, but to a journey. A journey that continues as long as curiosity persists, as long as questions outnumber answers, as long as the universe offers mysteries waiting to be explored. We have traveled far in this examination, from the initial excitement of discovery through the challenges of stellar activity and atmospheric loss, through the complexities of formation history and dynamical evolution, through the philosophical implications for life and intelligence, through the aspirational possibilities of interstellar travel and human expansion. Each layer has revealed new depths, new questions, new reasons to continue investigating. But there is still more to consider. The story of Proxima b does not exist in isolation. It connects to the broader story of exoplanet science, to the history of astronomy's expanding horizons, to the deep patterns that govern how stars and planets, and perhaps life itself, arise and evolve in the universe. These connections deserve exploration, for they place Proxima b in a context that illuminates its true significance. The next part of this journey will take us outward, from the specific details of one planetary system to the grand patterns that structure the cosmos. We will examine how the lessons from Proxima b inform our understanding of galactic habitability, how the evolution of the Milky Way shapes the conditions for life across billions of stars, and how the largest scales of cosmic structure connect to the smallest scales of planetary environments. The dark truth, it turns out, extends far beyond our nearest stellar neighbor into the deepest architecture of the universe itself. The Milky Way is not uniform. It is a structured environment where conditions vary enormously across its 100,000 light-year span, where some regions favor the emergence and persistence of life, while others remain forever hostile. This realization, emerging from decades of research into galactic structure and stellar populations, suggests that understanding any single planet requires understanding the cosmic address it occupies. Proxima b orbits a star in a particular location within the galaxy, a location that carries its own set of advantages and hazards. To fully appreciate what the dark truth about our nearest neighbor reveals, we must zoom out from the scale of planetary systems to the scale of galactic geography. The concept of the galactic habitable zone emerged in the early 2000s as astronomers began synthesizing knowledge about stellar populations, chemical evolution, and radiation environments across the Milky Way. Just as planets have habitable zones around their stars, the galaxy itself might have a habitable zone, a region where conditions favor the development of complex life. Too close to the galactic center, stellar densities are high, supernovae are frequent, and radiation bombardment is intense. Too far from the center, heavy element abundances drop, limiting the formation of rocky planets with the chemical complexity life requires. Somewhere between these extremes lies a band where conditions balance favorably. The Sun, and by extension, Proxima Centauri, orbits within this proposed galactic habitable zone. At roughly 26,000 light-years from the galactic center, our stellar neighborhood occupies a middle position in the disk, far enough from the chaotic central regions to avoid constant radiation assault, close enough to have accumulated sufficient heavy elements for rocky planet formation. This location might not be coincidental. It might represent a selection effect, where observers like us can only emerge in regions hospitable to complex life. But here's where the picture becomes more complicated. The galactic habitable zone, as originally conceived, was a static region with fixed boundaries. More recent modeling reveals a dynamic picture where habitable conditions migrate over cosmic time as the galaxy evolves. Early in the Milky Way's history, heavy element abundances were low everywhere. Rocky planets could form only after generations of stars had lived and died, seeding the interstellar medium with metals. The first habitable planets might have appeared 8 or 10 billion years ago, but only in the inner galaxy where star formation was most intense and chemical enrichment proceeded fastest. Over time, as metals diffused outward through stellar winds, supernovae, and galactic mixing, the habitable zone expanded, eventually reaching the solar neighborhood. This temporal evolution means that the conditions for life have not existed equally throughout the galaxy's history. Life might have arisen first near the galactic center, then spread outward as conditions permitted. Alternatively, the hostile radiation environment near the center might have prevented life from establishing there despite adequate chemistry, while the outer regions remained chemically immature. The pattern of life in the galaxy, if any exists, would reflect this evolutionary history, and this is where the study of Proxima b connects to galactic archaeology. The Alpha Centauri system's age, roughly 5 billion years, places its formation during a period when the solar neighborhood had already accumulated significant heavy elements. The system formed in an environment chemically capable of producing Earth-like planets. But conditions 5 billion years ago differed from conditions today in other respects. Supernova rates, cosmic ray fluxes, and background radiation levels have all changed as the galaxy evolved. The specific trajectory of the Alpha Centauri system through the galaxy also matters. Stars do not orbit the galactic center in simple circles. Their paths oscillate above and below the galactic plane, carry them through spiral arms, and occasionally bring them close to other stars or dense molecular clouds. Over billions of years, these wanderings expose planetary systems to varying environments. A passage through a spiral arm brings increased supernova rates and cosmic ray exposure. A close stellar encounter might gravitationally perturb planetary orbits. Proximity to a molecular cloud might compress the stellar wind, exposing planets to interstellar material. Reconstructing the orbital history of Alpha Centauri is challenging, but not impossible. Stellar kinematics, measured through proper motions and radial velocities, allow astronomers to trace stellar trajectories backward and forward in time. Such analyses suggest that Alpha Centauri has occupied a relatively stable region of the galactic disk, without dramatic excursions into hostile environments. The system has been relatively lucky, avoiding the worst hazards the galaxy can impose. Yet luck operates on timescales that dwarf human comprehension. Over the next billion years, the Alpha Centauri system's orbit will carry it through different galactic regions with different conditions. The habitability of Proxima b, whatever its current state, might change as cosmic radiation levels shift or as close stellar encounters perturb the planetary system. Habitability is not a permanent condition but a contingent one, subject to galactic as well as stellar influences. However, the deeper researchers examined galactic influences on habitability, the more they realized that local stellar environment matters as much as galactic location. Stars do not form in isolation. They form in clusters, dense aggregations of hundreds or thousands of stars that condense from molecular clouds and remain gravitationally bound for tens of millions of years before dispersing. The Sun almost certainly formed in such a cluster, along with thousands of sibling stars that have since scattered across the galaxy. Alpha Centauri likely formed in the same or a similar cluster, though whether the Sun and Alpha Centauri are true siblings remains uncertain. The birth cluster environment profoundly influences planetary systems. Close stellar encounters in dense clusters can strip away outer planets, disrupt protoplanetary disks, and even capture planets from neighboring stars. Massive stars in the cluster produce intense ultraviolet radiation that can photoevaporate disk material, limiting the resources available for planet formation. Supernovae from short-lived massive stars inject heavy elements, but also deliver devastating radiation to nearby systems. The details of a planetary system's birth cluster history shape its architecture and composition in ways that persist for billions of years. A system that formed in a sparse, quiet cluster would differ from one that formed in a dense, violent cluster, even if both ended up at similar galactic locations. For Proxima b, the unknown birth environment represents another layer of uncertainty in reconstructing its history and assessing its habitability. And this uncertainty extends to a question that has puzzled astronomers since Proxima Centauri's association with Alpha Centauri was first recognized. Did Proxima form together with Alpha Centauri A and B, or did it join the system later through gravitational capture? The evidence remains ambiguous. Chemical similarities suggest common origin. Kinematic properties are consistent with gravitational binding. But the wide separation between Proxima and the Alpha Centauri AB pair, over 13,000 astronomical units, makes the binding weak and raises questions about long-term stability. Simulations of stellar cluster dynamics show that both formation scenarios are plausible, neither proving nor ruling out shared origin. If Proxima was captured rather than co-formed, its planets might have experienced a more complex history. Capture events involve gravitational perturbations that could alter planetary orbits, excite eccentricities, or even strip away outer planets entirely. The current architecture of the Proxima system, with at least one close-in planet and possibly others at larger distances, would reflect both the system's original configuration and any modifications imposed during capture. But here's where the analysis becomes even more intricate. The timing of a hypothetical capture matters as much as whether capture occurred. If Proxima joined the Alpha Centauri system early, within the first 100 million years, when planet formation was still ongoing, The dynamical disturbance could have influenced how planets formed and migrated. If capture occurred later, after planet formation was complete, the effects would be limited to orbital perturbations rather than formational changes. The difficulty of distinguishing these scenarios illustrates a broader challenge in exoplanet science. We observe planetary systems as they exist today, but their current states result from billions of years of evolution shaped by processes we cannot directly observe. Reconstructing that evolution requires models that make assumptions, and different assumptions lead to different conclusions. The uncertainty is not a failure of science, but an inherent feature of studying systems whose histories are not directly accessible. Yet even within uncertainty, constraints accumulate. Each observation, each model refinement, each comparative study of other planetary systems narrows the range of possibilities. What we cannot know precisely, we can often bound statistically. The goal is not perfect knowledge, but progressively better knowledge, reduced uncertainty rather than complete certainty. And this brings us to another dimension of the galactic context, one that involves the distribution of stellar types across the Milky Way and its implications for the prevalence of habitable worlds. M-dwarfs, like Proxima Centauri, dominate the stellar population everywhere in the galaxy. Their abundance reflects fundamental physics of star formation, which produces far more low mass than high mass stars. The initial mass function, describing how stellar masses distribute in newly forming populations, follows a power law that heavily favors small stars. For every sun-like star that forms, roughly 10 M-dwarfs form. This ratio holds across the galaxy, in spiral arms and inter-arm regions, in old stellar populations and young ones. The dominance of M-dwarfs has profound implications for galactic habitability. If planets around red dwarfs struggle to maintain habitable conditions, as the study of Proxima b and similar systems suggests, then the vast majority of the galaxy's planets might be inhospitable. The habitable fraction would concentrate around the minority of sun-like stars, reducing the overall density of potentially life-bearing worlds. However, even this reduced density implies enormous absolute numbers. The Milky Way contains roughly 200 to 400 billion stars. If even 1% are sun-like G-dwarfs, that amounts to several billion stars. If 10% of those host habitable planets, hundreds of millions of potentially habitable worlds remain. The galaxy could be largely inhospitable, dominated by sterile M-dwarf systems, yet still contain more potential biospheres than humanity could ever explore. This statistical perspective matters for interpreting the silence of the cosmos. A galaxy with hundreds of millions of habitable planets might seem like it should be teeming with life. Yet if those planets are separated by hundreds or thousands of light years, communication and contact become extraordinarily difficult. The nearest habitable worlds around sun-like stars might be tens of light years away, requiring decades for even light-speed signals to travel each direction. Civilizations might exist in abundance, yet never encounter each other, separated by vast gulfs of space and time. Proxima b's proximity disrupts this picture of isolation. If the nearest star system to the Sun hosts a potentially habitable planet, perhaps habitable worlds are more common than the statistics suggest. Perhaps the conditions around M-dwarfs are more favorable than current models indicate. Perhaps we are merely in the early stages of understanding, and future observations will reveal a galaxy more hospitable than it currently appears. Or perhaps Proxima b is a statistical fluke, a potentially habitable world that happens to exist nearby, but represents a rare exception rather than a common case. The sample size of 1 provides no statistical power to distinguish these possibilities. Only by characterizing many more systems can we determine whether Proxima b is typical or exceptional. And this is where the next generation of exoplanet surveys becomes crucial. Missions like Plato, the European Space Agency's planetary transits and oscillations of stars mission, scheduled for launch in 2026, will search for Earth-sized planets around Sun-like stars, complementing the M-dwarf-focused surveys of Kepler and TESS. By building a sample of potentially habitable planets around different stellar types, Plato will enable statistical comparisons that constrain habitability across the stellar mass spectrum. Ground-based radial velocity surveys continue to discover new planets around nearby stars. The espresso spectrograph at the Very Large Telescope achieves precision sufficient to detect Earth-mass planets in habitable zones around quiet stars. The upcoming Terra hunting experiment will monitor nearby Sun-like stars for a decade, seeking the tiny wobbles produced by Earth analog planets. Each discovery adds to the census, building the statistical foundation needed to answer questions about habitability. But surveys provide only detection. Characterization requires follow-up observations that probe atmospheric composition, surface conditions, and potential biosignatures. The facilities for such characterization, extremely large ground telescopes, and next-generation space observatories, are still under construction or in planning phases. The full picture of galactic habitability will emerge only over decades as technology advances and data accumulates. Yet even as we await those future observations, theoretical work continues to illuminate the factors that determine habitability. And one factor that has gained increasing attention involves the role of planetary system architecture in shaping long-term environmental stability. The solar system's architecture appears unusually orderly compared to many exoplanetary systems. The planets occupy roughly circular orbits with low eccentricities and low inclinations. The spacing between planets follows regular patterns. Giant planets reside in the outer system, while rocky planets occupy the inner system. This orderly arrangement has persisted for over 4 billion years, providing Earth with a stable orbital environment throughout the history of life. Many exoplanetary systems exhibit far more chaotic architectures. Hot Jupiters, giant planets in extremely close orbits, must have migrated inward through regions where smaller planets might have formed, potentially destroying or scattering those worlds. Systems with highly eccentric orbits experience dramatic variations in stellar radiation as planets swing between close approaches and distant retreats. Compact systems with multiple planets in tight configurations might be dynamically unstable over long timescales, heading toward eventual collisions or ejections. The Proxima system's architecture remains incompletely known. Proxima b occupies a close orbit consistent with tidal locking. The candidate planet Proxima c, if real, orbits much farther out. The candidate Proxima d orbits even closer than Proxima b. If this architecture is accurate, the system contains planets spanning a wide range of orbital distances, but the relationships between them, the resonances, the stability, the potential for dynamical evolution remain unclear. What we can say is that the system has apparently persisted for nearly 5 billion years without catastrophic instability. Whatever interactions occurred, whatever migration or scattering took place. The current configuration represents a stable or metastable state. This survival implies some degree of orbital stability, though it does not guarantee that stability will persist indefinitely. And here's where long-term dynamical simulations provide insight. Researchers have modeled the Proxima system's evolution over billions of years, testing whether the observed or hypothesized planetary architectures remain stable. The results suggest that current configurations are generally stable, with low probabilities of planet-planet collisions or ejections over the remaining lifetime of the star. However, the simulations depend on assumptions about planetary masses, eccentricities, and inclinations that remain uncertain. Different assumptions yield different stability conclusions. The broader lesson is that planetary system stability is not guaranteed. Architectures that appear stable might contain hidden instabilities that manifest only over very long timescales. The solar system itself might experience instability billions of years hence, with Mercury potentially colliding with Venus or being ejected from the system. If such events occur commonly across exoplanetary systems, long-term habitability might be rarer than short-term habitability, with many worlds experiencing catastrophic disruptions at some point in their histories. For Proxima b, this raises questions about past stability as well as future stability. Did the current orbital configuration result from a calm, orderly formation process, or from violent scattering events that left Proxima b as a survivor among formerly more numerous siblings? The answer influences how we interpret the planet's history and its potential for hosting life. However, there is another factor in the galactic habitability equation that researchers have only recently begun to appreciate fully: the role of interstellar medium interactions in shaping planetary environments over cosmic time. The space between stars is not empty. It contains a diffuse medium of gas and dust, mostly hydrogen and helium, with trace amounts of heavier elements. This interstellar medium varies in density and composition across the galaxy, from dense molecular clouds where new stars form to hot, tenuous regions cleared by supernova explosions. As stars orbit the galactic center, they pass through different phases of the interstellar medium, encountering varying conditions over millions of years. When a star passes through a dense region of the interstellar medium, the pressure of that medium compresses the stellar wind, shrinking the protective bubble that shields the planetary system from interstellar particles. In extreme cases, the interstellar medium might penetrate deep into the system, reaching the inner planets and depositing gas, dust, and cosmic rays directly onto planetary surfaces and atmospheres. Such encounters leave geological and chemical signatures. Terrestrial ice cores and deep-sea sediments record variations in cosmic ray flux over millions of years, revealing episodes when the solar system passed through denser interstellar regions or encountered the debris of nearby supernova. These records show that Earth has experienced significant environmental perturbations from galactic sources, though none severe enough to cause mass extinctions on their own. For Proxima b, the effects of interstellar medium interactions depend on the properties of Proxima Centauri's stellar wind and the local interstellar environment. The stellar wind from an M-dwarf is different from the solar wind, with different density, velocity, and magnetic field characteristics. The protective bubble it creates, the astrosphere, might be larger or smaller than the sun's heliosphere depending on these properties. If the astrosphere is small, Proxima b might be more exposed to interstellar influences than Earth has been. Recent observations by spacecraft like Voyager, which have crossed the boundary of the heliosphere and entered interstellar space, provide direct measurements of the local interstellar medium's properties. These measurements constrain models of how stellar winds interact with their environments, improving our understanding of astrospheric dynamics around other stars. For Proxima, direct measurement is impossible with current technology, but models informed by solar system data offer estimates. The emerging picture suggests that Proxima b resides within its star's astrosphere under normal conditions, protected from the full flux of interstellar cosmic rays. However, during passages through unusually dense interstellar clouds, or in the aftermath of nearby supernovae, the astrosphere might compress sufficiently to expose the planet directly. Such events would be rare, perhaps occurring once every few hundred million years, but their cumulative effects over billions of years could be significant. And this introduces yet another factor in the habitability calculus. Not just the star's activity, not just the planet's orbital dynamics, not just atmospheric chemistry and geological processes, but also the external environment through which the entire system moves over cosmic time. Habitability is not merely a property of a planet, but of a planet in context, embedded in a planetary system, which is embedded in a stellar neighborhood, which is embedded in a galaxy, which evolves over billions of years. This multi-layered complexity might seem to make the problem of assessing habitability intractable. So many factors, so many uncertainties, so many processes interacting across such vast ranges of scale in space and time. How can we possibly evaluate whether any given planet can support life? The answer lies in the statistical approach. We cannot determine with certainty whether Proxima b is habitable, but we can assess probabilities. We can identify factors that enhance or diminish habitability. We can model the ranges of outcomes given different assumptions, and we can update those probabilities as new observations constrain the parameters. This probabilistic framing is not a limitation, but a strength. It honestly reflects our state of knowledge while providing a framework for progress. Each new measurement, each refined model, each comparative study of other systems adjusts the probabilities, moving us toward better estimates of habitability for Proxima b and for the galaxy at large. But there is one more dimension to consider, one that has emerged from the most recent theoretical work on planetary habitability: the role of stochastic events, random occurrences that can either devastate or enhance a planet's prospects for life. The history of life on Earth is punctuated by random events that shaped evolutionary trajectories in ways that could not have been predicted. The asteroid impact that ended the Cretaceous period and triggered the extinction of the dinosaurs is the most famous example, but others abound. The snowball Earth episodes of the Neoproterozoic, when the planet apparently froze over entirely, nearly extinguished life before the rise of complex organisms. The Great Oxidation Event, when photosynthetic organisms flooded the atmosphere with oxygen, was a biologically driven catastrophe that killed most existing life while enabling entirely new forms to emerge. These events were not deterministic outcomes of planetary processes. They were contingencies, accidents of timing and circumstance that could have unfolded differently with different results. If the asteroid had missed, dinosaurs might still dominate Earth. and mammals might never have diversified into their current forms. If the snowball Earth had lasted slightly longer or been slightly more severe, the eukaryotic lineages that would eventually give rise to complex life might have perished. For Proxima b, similar contingencies might have occurred, determining whether life arose, whether it persisted, whether it evolved complexity. A slightly different impact history, a slightly different pattern of stellar flares, a slightly different composition of the primordial atmosphere. Any of these could have pushed the planet's trajectory toward habitability or sterility. We cannot know which contingencies actually occurred. We can only recognize that they occurred, that Proxima b's current state reflects not just deterministic processes, but also random events whose outcomes were not foreordained. This stochastic dimension adds irreducible uncertainty to habitability assessments. Even if we knew all the deterministic factors perfectly, even if we could model stellar activity and atmospheric chemistry and geological processes with complete accuracy, the random events that shaped a planet's history would remain unknown. The best we can achieve is probabilistic understanding, knowledge of the likelihood of different outcomes given the range of possible contingencies, and yet stochasticity also offers hope. If random events play significant roles, then even planets facing unfavorable deterministic conditions might be rescued by fortunate accidents. A late delivery of volatiles, a period of unusual stellar quiescence, a geological event that released atmospheric gases at a critical moment. Any of these could have transformed a hostile world into a habitable one. We cannot predict such events, but we cannot rule them out either. For Proxima b, this means maintaining appropriate humility about confident conclusions. The planet faces significant challenges. The stellar activity is hostile. The radiation environment is harsh. The atmospheric prospects are uncertain. By the deterministic factors we can model, habitability seems unlikely. But the contingencies we cannot model might have intervened. The planet might have caught breaks that compensated for its disadvantages. Only direct observation can reveal the actual outcome. The universe is under no obligation to match our models. It does what it does, indifferent to our expectations. Scientific inquiry is the process of updating expectations to match reality, revising models when observations contradict predictions, and embracing surprise as an opportunity for learning. Proxima b might surprise us. That possibility, however slim, justifies continued observation and continued openness to unexpected results. As we approach the conclusion of this examination, the scope has expanded enormously from where we began. What started as a story about one planet orbiting the nearest star has grown to encompass stellar activity, atmospheric physics, orbital dynamics, galactic structure, cosmic evolution, and the philosophy of scientific knowledge. The dark truth about Proxima b was indeed only the beginning, the first indication of how deep the questions go and how far the implications reach. Yet even this expanded scope does not exhaust the subject. There remain dimensions we have not explored, connections we have not traced, implications we have not considered. The story of Proxima b connects to the story of planetary science, which connects to the story of astronomy, which connects to the story of physics, which connects to the most fundamental questions about the nature of reality. Every scientific inquiry, pursued deeply enough, touches these ultimate questions. In the next part of this exploration, we will turn to the most profound implications of what we have learned. What does the study of Proxima b reveal about the nature of habitability itself, as a concept and as a physical phenomenon? How should we think about the prospects for life in a universe where conditions vary so enormously and contingencies play such significant roles? And what does the search for life beyond Earth tell us about ourselves, about our place in the cosmos, and about the meaning of existence in an apparently indifferent universe? These questions carry us beyond science into philosophy, beyond observation into reflection. Yet they arise naturally from the scientific investigation we have conducted. The dark truth about Proxima b is not merely a set of facts about stellar activity and atmospheric chemistry. It is an invitation to think deeply about life, intelligence, and the cosmic context in which both arise. That invitation, extended by a small planet orbiting a dim red star 4 light-years away, deserves a thoughtful response. The question of what makes a world habitable seems straightforward until you try to define it precisely. We speak of habitable zones and habitable conditions as if habitability were a binary property, something a planet either possesses or lacks. Yet the more we study planetary environments, the more this binary framing reveals its limitations. Habitability exists on a continuum, varying in degree rather than kind, dependent on perspective rather than absolute standards. A world habitable for extremophilic bacteria might be lethal to mammals. A world hospitable to silicon-based chemistry, if such chemistry is possible, might be completely hostile to carbon-based life. The concept itself requires examination before we can meaningfully apply it to worlds like Proxima b. Let us explore what habitability truly means, how our understanding of it has evolved, and what the study of extreme environments on Earth reveals about the possibilities elsewhere. The traditional definition of habitability centers on liquid water. Water serves as Earth's universal solvent, the medium in which biochemical reactions occur, the essential ingredient for life as we know it. The habitable zone around a star is defined as the range of distances where a planet's surface temperature could permit liquid water to exist. This definition has guided exoplanet research for decades, providing a simple criterion for sorting discovered worlds into interesting and less interesting categories. Yet liquid water is merely a necessary condition, not a sufficient one. A planet with surface water might still be uninhabitable if other factors preclude life. The wrong atmospheric composition, the absence of essential nutrients, the presence of sterilizing radiation, the lack of energy sources to drive metabolism, any of these could render a water-rich world sterile. Conversely, a planet without surface water might still harbor life in subsurface oceans, in atmospheric layers, or in exotic environments we have not yet imagined. The water-centric definition also reflects Earth-centric bias. We focus on water because terrestrial life requires it, but we cannot know whether life elsewhere might use different solvents. Ammonia remains liquid at much lower temperatures than water and could theoretically serve as a biochemical medium on cold worlds. Liquid hydrocarbons, like the methane and ethane lakes on Saturn's moon Titan, offer another possibility. Even more exotic solvents, sulfuric acid, supercritical carbon dioxide, liquid nitrogen, appear in theoretical discussions of alternative biochemistries. None of these alternatives has been demonstrated to support life, but our sample size of 1 provides no basis for ruling them out. For Proxima b, the water-centric habitability question remains open. The planet might possess water either on its surface or in its interior, depending on formation history and subsequent evolution. It might have lost any primordial water to stellar activity and space weathering. It might exist in a state between these extremes, with water locked in minerals or subsurface reservoirs inaccessible to remote observation. Each possibility carries different implications for potential biology. But here's where the concept of habitability encounters deeper complications. Even if Proxima b possesses liquid water in abundance, the environment might be hostile in ways that prevent life from arising or persisting. Consider the energy requirements for life. Terrestrial organisms derive energy from two primary sources: sunlight, captured through photosynthesis, and chemical reactions, exploited through chemosynthesis. Photosynthesis requires light at wavelengths organisms can capture and convert. Chemosynthesis requires chemical gradients, differences in concentration or oxidation state that can be harnessed for energy. A planet might have liquid water, yet lack accessible energy sources, leaving any potential life without the fuel needed for metabolism. For Proxima b, the energy question is complicated by the star's spectrum. M dwarfs emit most of their radiation at red and infrared wavelengths, with relatively little in the blue and ultraviolet. Terrestrial photosynthesis uses primarily red and blue light, with chlorophyll absorbing most efficiently at specific wavelengths. Organisms on Proxima b would need different pigments, adapted to capture the available wavelengths from a red dwarf star. Such adaptation is biologically plausible. Some terrestrial organisms use pigments that absorb infrared light, but it represents a constraint on possible biology. The lower ultraviolet output of M dwarfs might seem advantageous, reducing photo damage to organic molecules. However, ultraviolet light also drives prebiotic chemistry, the reactions that might have produced life's building blocks on early Earth. Too little ultraviolet radiation could slow or prevent the chemical evolution leading to life's origin. The balance between protection and chemistry depends on details of atmospheric composition and surface conditions that remain unknown for Proxima b. And this is where the study of Earth's extreme environments illuminates possibilities elsewhere. Over the past half-century, biologists have discovered life in environments once thought completely sterile. The deep ocean hydrothermal vents, where superheated water laden with minerals erupts from the sea floor, support thriving ecosystems based on chemosynthesis rather than photosynthesis. The deep continental subsurface, kilometers below Earth's surface, harbors microbial communities living in rock fractures and aquifers, isolated from the surface for millions of years. Antarctic ice, acidic hot springs, hypersaline lakes, the interiors of radioactive waste sites. Every extreme environment examined has revealed life adapted to conditions that would kill most organisms. These discoveries have progressively expanded the known limits of habitability. Temperature extremes from -20 degrees Celsius to over 120 degrees Celsius support some form of life. pH ranges from near 0 to above 12 are tolerated. Radiation doses thousands of times higher than would kill humans leave certain bacteria unharmed. Desiccation, high pressure, low nutrient availability, all have proven surmountable for appropriately adapted organisms. The implications for exoplanet habitability are profound. If life can persist under such extreme conditions on Earth, similar conditions on other planets might also be habitable. The envelope of possible habitats extends far beyond the comfortable surface environments where humans thrive, encompassing subsurface oceans, high-altitude atmospheres, and chemical environments that seem hostile by human standards. For Proxima b, this expanded envelope offers cautious hope. Even if the surface is inhospitable, even if stellar activity has stripped the atmosphere and baked the rocks with radiation, protected environments might exist. A subsurface ocean, warmed by residual internal heat or tidal dissipation, would be shielded from stellar flares. Organisms living in that ocean would be oblivious to conditions on the surface, evolving in darkness according to their own trajectory. However, the deeper researchers examined Earth's extremophiles, the more they recognized an important caveat. These organisms are adapted to extreme conditions, but they did not originate under those conditions. Life on Earth arose in more moderate environments, likely in warm, shallow waters or around hydrothermal vents with access to chemical energy. Only later did life colonize extreme environments, carrying with it the biochemical machinery developed under more favorable conditions. This distinction matters because the origin of life might require conditions different from those needed for life's persistence. A planet habitable for existing life might not be habitable for the origin of new life. If Proxima b's conditions prevent life from arising in the first place, the planet would remain sterile, regardless of whether extremophiles could survive there if transported from elsewhere. The origin of life remains one of science's greatest unsolved problems. We do not know precisely how non-living chemistry gave rise to the first self-replicating systems on Earth. Multiple hypotheses compete, involving hydrothermal vents, warm ponds, ice matrices, or mineral surfaces. Each hypothesis implies different environmental requirements, different chemical conditions, different timescales for the transition from chemistry to biology. For Proxima b, the origin question intersects with the planet's early history. Did conditions ever permit the chemical evolution leading to life? If the planet formed with a thick atmosphere that was later stripped away, was there a window of opportunity before the stripping occurred? If tidal heating maintained geological activity, did that activity create the chemical gradients needed for prebiotic chemistry? These questions cannot be answered with current data. They require understanding the planet's entire evolutionary trajectory, not just its current state. And yet, there is another possibility that sidesteps the origin question entirely. Life might not need to originate on each world separately. It might spread between worlds, colonizing new planets from existing biospheres. The concept of panspermia, life spreading through space, has a long history in scientific speculation. In its simplest form, panspermia suggests that microorganisms might survive transport between planets via meteorites, asteroids, or comets. An impact on a life-bearing world ejects material into space. Some of that material carries viable organisms protected within rock fragments from radiation and temperature extremes. Eventually, some fragments land on other worlds, potentially seeding new biospheres. Evidence for the plausibility of panspermia has accumulated over decades. Meteorites from Mars have been identified in terrestrial collections, demonstrating that material exchange between planets occurs. Laboratory experiments show that certain bacteria can survive the conditions of space, including vacuum, radiation, and temperature cycling for extended periods. The deep, subsurface environments where hardy microorganisms live would be precisely the environments shielded within meteorites during interplanetary transit. For the Alpha Centauri system, panspermia raises intriguing possibilities. If life exists on Proxima b, it might have originated there, or it might have arrived from elsewhere, perhaps from a moon of Proxima c, or from debris exchanged with the Alpha Centauri AB system during close approaches. The 4 light-year distance from the solar system makes direct exchange between Earth and Proxima b extremely unlikely, given the long transit times and harsh interstellar conditions, but exchange within the Alpha Centauri system itself is more plausible. If panspermia operates, then discovering life on Proxima b would not necessarily mean life originated there. The life might share common ancestry with biospheres elsewhere in the Alpha Centauri system, or even, in the most speculative scenarios, with life elsewhere in the galaxy. This possibility complicates the interpretation of any future detection. Finding life on Proxima b would be revolutionary, but understanding that life's origin would require additional investigation. But here's where the conceptual territory becomes even more complex. The discussion so far has assumed life as we understand it, based on organic chemistry, dependent on solvents and energy sources, evolving through natural selection. What if life can take forms so different that we would not recognize them as alive? The definition of life itself is contested. Biologists generally agree on certain properties: metabolism, reproduction, evolution, response to environment. But these properties describe terrestrial life and might not capture all possible forms. Could there be life based on information patterns rather than physical substrates? Could magnetic fields or plasma configurations in stellar atmospheres exhibit lifelike properties? Could the complex dynamics of planetary weather systems or geological processes cross some threshold into a form of living organization? These questions venture into speculation, but they serve a purpose. They remind us that our concepts are derived from a single example and might not generalize. When we search for life on Proxima b or anywhere else, we search for what we know how to look for. If life exists in forms radically different from terrestrial biology, we might fail to recognize it, even if we observed it directly. This limitation shapes search strategies. We look for biosignatures, chemical indicators of biological activity, because we know what chemistry terrestrial life produces. Oxygen, methane, nitrous oxide. These gases and disequilibrium combinations suggest active biology, but an alien biosphere, based on different chemistry, would produce different signatures, perhaps signatures we would not recognize as biological. The absence of familiar biosignatures does not prove the absence of life, only the absence of life similar to Earth's. For Proxima b, this means that even comprehensive atmospheric characterization might not settle the life question. We might detect an atmosphere with no obvious biosignatures and conclude the planet is probably sterile, while exotic life forms thrive undetected. Or we might detect signatures that suggest biology, but could also result from abiotic processes we have not considered. The interpretation of observations requires assumptions, and those assumptions might be wrong. And yet, science must work with what it has. We cannot search for what we cannot define or detect. The strategy of looking for Earth-like biosignatures makes sense given our current knowledge, even acknowledging its limitations. As our understanding expands, search strategies will evolve, incorporating new possibilities and new detection methods. The search for life is not a single investigation, but an ongoing program that adapts as knowledge grows. This adaptive quality characterizes all scientific inquiry. We begin with what we know, formulate questions based on current understanding, and revise our approach as new evidence and ideas emerge. The study of Proxima b exemplifies this process. Initial assessments based on habitable zone calculations have given way to more nuanced evaluations, incorporating stellar activity, atmospheric dynamics, and planetary evolution. Future assessments will incorporate factors we have not yet recognized as important. Let us now consider another dimension of habitability that has received increasing attention in recent years: the role of planetary magnetic fields in protecting atmospheres and surfaces from harmful radiation. Earth's magnetic field arises from convection in the liquid iron outer core, driven by heat loss from the inner core and the planet's rotation. This geodynamo generates a dipolar field that extends into space, deflecting the solar wind and trapping charged particles in radiation belts. Without this magnetic shield, the solar wind would directly impact the upper atmosphere, stripping away lighter gases and exposing the surface to harmful particle radiation. The importance of magnetic fields for habitability has been debated. Mars, which lacks a global magnetic field today, has lost most of its atmosphere over billions of years, though whether the absence of a field was the primary cause remains uncertain. Venus, also lacking a strong intrinsic field, retains a thick atmosphere despite receiving more solar wind than Earth. The relationship between magnetic fields and atmospheric retention depends on multiple factors, including atmospheric composition, gravity, stellar wind properties, and the presence of induced magnetic fields from atmospheric ionization. For Proxima b, the magnetic field question is critical but unanswerable with current technology. We cannot directly measure the magnetic fields of exoplanets. We can only infer possibilities based on planetary properties and theoretical models of dynamo generation. Tidal locking works against strong magnetic fields. A tidally locked planet rotates slowly, once per orbit rather than many times per orbit. Slow rotation reduces the efficiency of dynamo generation, potentially weakening the magnetic field or preventing its formation entirely. Some models suggest tidally locked planets might have fields only 10% as strong as Earth's, insufficient to deflect the intense stellar winds from active M-dwarfs. However, other factors might compensate. If Proxima b has a large liquid core, the greater volume of conducting fluid could partially offset the slow rotation. If the core composition differs from Earth's, perhaps enriched in lighter elements that remain liquid at lower temperatures, the dynamo might operate more efficiently. If tidal heating maintains vigorous convection in the core, magnetic field generation might persist despite slow rotation. The uncertainty illustrates a recurring theme. We know what factors matter for habitability, but we cannot measure those factors for distant exoplanets. Theory provides ranges of possibilities, but observation cannot yet select among them. This gap between what we need to know and what we can measure defines the current state of exoplanet habitability assessment. Yet the gap is narrowing. New observational techniques offer hope for detecting exoplanetary magnetic fields indirectly. Radio emissions from interactions between stellar winds and planetary magnetospheres might be detectable with sensitive radio telescopes. Auroral emissions produced when charged particles impact atmospheric molecules could reveal magnetic field geometries. Transit observations might detect asymmetries caused by magnetospheric structures. None of these techniques has yet definitively detected an exoplanetary magnetic field, but ongoing development brings detection closer. For Proxima b, radio observations represent a particularly promising avenue. The planet's proximity means any magnetospheric radio emissions would be stronger at Earth than emissions from more distant exoplanets. Several observing campaigns have searched for such emissions without success, but upper limits have progressively tightened. Either Proxima b lacks a strong magnetic field, or its field geometry produces emissions below current detection thresholds, or the emissions occur at frequencies or times not yet observed. The search continues as it must. Each non-detection constrains possibilities. Each new instrument opens parameter space previously inaccessible. The iterative nature of scientific investigation means that questions unanswerable today might be answered tomorrow as technology advances and observations accumulate. And this brings us to consider the timescales over which habitability must be maintained for life to arise, persist, and evolve complexity. The origin of life on Earth occurred relatively quickly in geological terms. Evidence of microbial life appears in rocks dating to at least 3.5 billion years ago, and possibly earlier. Since Earth formed 4.5 billion years ago and remained largely molten for several hundred million years, the window for life's origin was perhaps 500 million years or less. This suggests that the transition from chemistry to biology might occur rapidly given appropriate conditions. Though with a sample of 1, we cannot know whether Earth was typical or unusually lucky. The evolution of complex life, in contrast, required far longer. Single-celled organisms dominated Earth for over 2 billion years before the first eukaryotes appeared. Multicellular life emerged only around 600 million years ago. Complex animals, plants, and fungi diversified during the Cambrian explosion, roughly 540 million years ago. Intelligent life, capable of wondering about other planets, appeared only in the last few million years, a blink in geological time. These timescales carry implications for exoplanet habitability. A planet must remain habitable, not just for millions of years, but for billions of years to produce complex life. Short-term habitability might allow microbial ecosystems to establish, but only long-term stability permits the evolutionary accumulation leading to complexity and intelligence. For Proxima b, the question becomes whether the planet has maintained habitable conditions, in whatever niche, continuously for billions of years. The episodic superflares from Proxima Centauri pose a challenge. If each major flare sterilizes the surface, any surface life must repeatedly re-establish from protected refugia or re-evolve from scratch. Such repeated disruptions might prevent the long evolutionary chains needed for complexity. However, subsurface environments face no such disruption. Life in a subsurface ocean would be insulated from surface catastrophes, free to evolve continuously over billions of years. The evolution might proceed slowly in the energy-poor deep environment, but the time available is vast. Even slow evolution over 4 billion years could produce substantial complexity. And here's where comparative planetology offers perspective. Earth is not the only body in our solar system where life might exist or might have existed. Mars shows evidence of past liquid water and might harbor subsurface life today. Europa and Enceladus possess subsurface oceans that could support chemosynthetic ecosystems. Titan has a complex organic chemistry and liquid hydrocarbon lakes that might host exotic life forms. Each of these worlds represents a different test case for habitability, a different set of conditions under which life might arise or persist. The exploration of these solar system bodies directly informs our expectations for exoplanets. If we find life on Mars, it would suggest that life arises readily given liquid water and chemical energy. If we find nothing on Mars, despite past habitability, it might indicate that life's origin is rare, even under favorable conditions. If Europa's ocean hosts ecosystems, subsurface habitability becomes a confirmed phenomenon, rather than mere speculation. Each discovery or non-discovery adjusts our priors for what to expect at Proxima b and elsewhere. The coming decades will bring unprecedented exploration of these solar system targets. NASA's Europa Clipper mission, launched recently, will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. The Dragonfly mission to Titan, planned for the 2030s, will explore the moon's surface chemistry with a rotorcraft lander. Mars sample return missions aim to bring Martian rocks to Earth for detailed analysis that might reveal signs of past or present life. These missions represent humanity's first systematic search for life beyond Earth, a search that will inform exoplanet investigations for generations. But the study of Proxima b need not wait for solar system results. The two investigations proceed in parallel, each informing the other. Discoveries about Proxima b's atmosphere, or surface conditions, constrain what kinds of life might exist there, guiding what biosignatures to seek. Discoveries about life in the solar system constrain what conditions life requires, guiding how to interpret Proxima b observations. The investigations are complementary, not sequential. And this parallel approach reflects a broader truth about scientific inquiry. Knowledge does not advance along a single front, but across many fronts simultaneously. Insights from one area inform questions in another. Techniques developed for one purpose find application elsewhere. The community of researchers is interconnected, sharing methods and results across disciplinary boundaries. The study of Proxima b draws on stellar physics, planetary science, atmospheric chemistry, astrobiology, and observational astronomy, each contributing pieces to a puzzle that none could solve alone. This interdisciplinary character makes exoplanet science intellectually rich and practically challenging. Experts in different fields must communicate across different technical languages and different research cultures. Synthesizing knowledge from diverse sources requires breadth as well as depth, a willingness to engage with unfamiliar territory. The researchers who have advanced our understanding of Proxima b have navigated this complexity, combining expertise from multiple domains to construct a coherent picture, yet the picture remains incomplete. Major questions persist. Does Proxima b have an atmosphere? If so, what is its composition? Is there liquid water on the surface or below? Is there geological activity? Is there a magnetic field? Has the planet maintained habitable conditions over geological time? Could life have arisen? Could life exist today? Each question awaits answers that future observations and future missions might provide. The waiting is part of science. Unlike fields where experiments can be conducted quickly and results obtained rapidly, astronomy operates on timescales set by nature and technology. Building new telescopes takes decades. Securing observing time takes years. Analyzing data takes months. The rhythm is slow by human standards, demanding patience that not all possess. But the questions are profound, and the eventual answers will be worth the wait. As we approach the final part of this exploration, the threads we have followed begin to converge. The dark truth about Proxima b, initially a story about hostile stellar activity and challenging planetary conditions, has expanded into a meditation on habitability, life, and humanity's place in the cosmos. The specific details of one planet orbiting one nearby star have illuminated principles that apply throughout the galaxy. The questions we ask about Proxima b are the questions we ask about the universe itself. In the concluding part, we will draw these threads together, considering what we have learned, what remains unknown, and what the investigation of Proxima b reveals about the scientific enterprise and the human quest for understanding. The dark truth was only the beginning. The beginning leads to depths we have only begun to explore. And the exploration, whatever it ultimately reveals, represents one of humanity's most profound endeavors. The attempt to understand our cosmic context and our potential cosmic companions. We have traveled far in this exploration, from the initial discovery of a world orbiting our nearest stellar neighbor to the deepest questions about life, habitability, and humanity's place in the cosmos. The journey has taken us through stellar physics and atmospheric chemistry, through planetary dynamics and galactic structure, through the philosophy of scientific knowledge and the nature of life itself. What began as a straightforward story about a potentially habitable exoplanet revealed itself to be something far more profound, an invitation to reconsider fundamental assumptions about where life can exist and how we might find it. Now, as we draw these threads together, let us reflect on what the study of Proxima b has taught us and what it suggests about the path forward. The most immediate lesson concerns the complexity of habitability. The habitable zone, that elegant concept defining the region around a star where liquid water might exist, remains useful as a first approximation, but only as a first approximation. Real habitability depends on factors the habitable zone calculation does not capture: stellar activity, atmospheric retention, magnetic field protection, geological processes, orbital stability, and the countless contingencies that shape planetary evolution over billions of years. A planet within the zone might be habitable, or might face challenges that render it sterile. Location provides opportunity, but opportunity does not guarantee outcome. This complexity is not a disappointment, but an enrichment. Simple answers would close inquiry. Complex answers open it, revealing new questions to pursue, new factors to investigate, new connections to explore. The study of Proxima b has generated more questions than it has answered, and that proliferation of questions represents scientific progress. We understand more deeply what we do not know, which is the prerequisite for eventually knowing it. The second lesson concerns the relationship between particular cases and general principles. Proxima b is one planet around one star, but its significance extends far beyond that singular identity. It serves as a test case for understanding M-dwarf planetary systems, which constitute the majority of planetary systems in the galaxy. What we learn about Proxima b informs our expectations for thousands of similar worlds, too distant for detailed study. The particular illuminates the general, the nearby reveals the distant, the accessible unlocks the inaccessible. This scaling from particular to general characterizes much of science. We study what we can study, then extrapolate to what we cannot. The extrapolation carries uncertainty, which observation of additional cases progressively reduces. Proxima b is the first step in a long journey of characterizing potentially habitable exoplanets. Future observations of other systems will test whether the lessons from Proxima b apply broadly or reflect local peculiarities. Either outcome advances understanding. The third lesson concerns the timescales of scientific inquiry. The questions raised by Proxima b will not be answered quickly. The telescopes needed for definitive characterization are still under construction or still being planned. The observations will require years to complete and years more to analyze. The theoretical frameworks for interpretation continue to evolve. Decades might pass before we know with confidence whether Proxima b possesses an atmosphere, whether that atmosphere contains biosignatures, whether the planet has ever been habitable in any meaningful sense. This extended timescale requires patience and institutional commitment that span human generations. The researchers who first detected Proxima b might not live to see the definitive characterization of its environment. The students beginning their careers today might complete theirs before the key questions find answers. Science, particularly astronomy, operates on rhythms that exceed individual human lifetimes, requiring structures that persist and commitments that endure beyond any single investigator. Yet this multi-generational character is not unique to the study of Proxima b. It reflects the nature of profound questions, which rarely yield to quick investigation. The easy questions have already been answered. What remains are the hard questions, the deep questions, the questions whose answers require decades or centuries of accumulated effort. The study of Proxima b joins the study of cosmic structure, of fundamental physics, of the origin of life, as an inquiry whose completion lies beyond any horizon we can see. And this brings us to a broader reflection on what such inquiry represents in human terms. The desire to understand the cosmos, to know whether life exists beyond Earth, to comprehend our place in the vast architecture of the universe, runs deep in human consciousness. Every culture has looked at the night sky and wondered. Every generation has asked whether we are alone. The questions predate science by millennia, emerging from something fundamental in human nature, a curiosity that seeks to understand not just the immediate and practical, but the distant and profound. Science has transformed these ancient questions from speculation into investigation. We no longer merely wonder about other worlds. We detect and characterize them. We no longer merely imagine life elsewhere. We develop strategies to search for it systematically. The questions remain the same, but the methods have changed. From myth and philosophy to observation and experiment. This transformation represents one of humanity's great intellectual achievements, the development of systematic methods for interrogating nature and obtaining reliable answers. The study of Proxima b exemplifies this achievement, a world 4 light-years distant, invisible to the naked eye, orbiting a star too dim to see without telescopes, has become an object of detailed scientific investigation. We know its orbital period, its minimum mass, its position relative to the habitable zone. We have constrained its atmospheric properties, modeled its climate, assessed its potential for supporting life. This knowledge, obtained through human ingenuity, applied to photons traveling across interstellar distances, represents an extraordinary extension of our senses and our understanding. Yet the knowledge remains incomplete, as all scientific knowledge does. We have learned much about Proxima b, but much more remains to learn. The incompleteness is not a failure, but a feature. Science is not a body of settled facts, but a process of ongoing inquiry. The questions answered generate new questions. The mysteries solved reveal deeper mysteries. The frontier of knowledge advances, but never reaches a final boundary. This endless frontier is not frustrating, but invigorating, offering each generation new territories to explore, new problems to solve, new understanding to achieve. For Proxima b specifically, the coming decades will bring observations that transform our understanding. The extremely large telescope and other ground-based giants will achieve angular resolutions and sensitivities far exceeding current capabilities. Space-based observatories optimized for exoplanet characterization will complement ground-based facilities. New detection methods, from radio observations of magnetospheric emissions to interferometric imaging of planetary surfaces, will provide data inaccessible today. The picture of Proxima b that emerges from these observations will be far richer than the picture we currently possess. Whether that picture includes signs of life remains to be seen. The challenges facing Proxima b, the stellar activity, the potential for atmospheric stripping, the effects of tidal locking, suggest that habitability is unlikely by conventional standards. But nature has surprised us before and might surprise us again. The discovery of extremophiles on Earth demonstrated that life tolerates conditions once thought impossible. The diversity of exoplanetary systems has exceeded what theorists predicted. Proxima b might confound expectations, harboring life in niches we did not anticipate, or maintaining habitability through mechanisms we have not modeled. The appropriate stance is neither optimism nor pessimism, but openness. We do not know what Proxima b will reveal, and we should not pretend otherwise. The honest acknowledgement of uncertainty is not intellectual weakness, but scientific strength. It permits revision in light of evidence, adaptation in response to discovery, learning from whatever nature presents. The researchers investigating Proxima b approach their subject with this openness, willing to be surprised, prepared to update their models, committed to following evidence wherever it leads. And this openness extends to the broader questions that Proxima b represents. Whether life exists beyond Earth, whether intelligence is common or rare, whether humanity will ever make contact with other minds, these questions remain genuinely open. We have hypotheses, arguments, estimates, but we lack definitive answers. The search continues because the questions matter, because the answers would reshape human self-understanding, because the inquiry represents something essential about who we are as a species. The search also continues because it is possible. We have developed the technologies to detect exoplanets, characterize their atmospheres, and search for biosignatures. We are developing technologies that might eventually send probes to nearby stars. The questions that once seemed forever beyond reach have become tractable, subject to investigation with instruments we can build and observations we can make. This tractability is recent, emerging only in the last few decades, and it represents a threshold crossed in human capability. For the first time in history, we can systematically search for life beyond Earth. That opportunity carries an obligation to pursue it. Yet the pursuit must be patient. The timescales are long, the challenges formidable, the uncertainties large. quick answers are unlikely. Definitive conclusions might take generations. The search for life around Proxima b, like the search for life elsewhere in the universe, is a marathon rather than a sprint, requiring sustained effort over extended periods. Those who contribute might not see the finish line. The contribution matters nonetheless, adding to an accumulating body of knowledge that future generations will inherit and extend. This multi-generational aspect connects the study of Proxima b to other great human projects. The construction of cathedrals, the compilation of dictionaries, the mapping of genomes, the exploration of continents. These endeavors share the quality of exceeding individual lifetimes while expressing collective aspiration. The participants contribute to something larger than themselves, something that will continue beyond them, something that embodies values and goals transcending immediate circumstances. The study of Proxima b belongs to this category of endeavor, expressing humanity's desire to understand its cosmic context and potentially its cosmic companions. The expression takes many forms: astronomers building instruments and making observations, theorists developing models and interpreting data, engineers designing missions and solving technical challenges, educators communicating discoveries and inspiring future researchers, funders providing resources, and institutions providing structure. The collective effort involves thousands of people across dozens of countries, united by shared curiosity and shared commitment to understanding. This collaboration represents one of humanity's better aspects, the capacity for cooperative inquiry in pursuit of knowledge that benefits all. And the benefits extend beyond the specific knowledge obtained. The technologies developed for exoplanet detection find applications elsewhere. The computational methods created for data analysis serve other purposes. The international collaborations established for astronomical research provide models for cooperation in other domains. The inspiration generated by discoveries about distant worlds motivates young people to pursue scientific careers. The indirect effects ripple outward, touching areas far removed from the original investigation. But perhaps the deepest benefit is philosophical rather than practical. The study of Proxima b and similar worlds reminds us of our cosmic context. Our position as inhabitants of a small planet, orbiting an ordinary star in an unremarkable region of one galaxy among billions. This perspective, often called the cosmic perspective, provides counterweight to the provincial concerns that dominate daily life. The problems that seem overwhelming shrink when viewed against the backdrop of cosmic time and space. The conflicts that divide humanity seem trivial when compared to the vast unity of physical law governing the entire universe. The cosmic perspective does not solve our problems, but it contextualizes them, providing a frame within which their true proportions become visible. Proxima b contributes to this perspective by making the cosmic tangible. It is not an abstraction, but a specific world, a place with defined properties orbiting a specific star at a specific distance. We can point to it even if we cannot see it with unaided eyes. We can discuss its properties in concrete terms, not as speculation, but as constrained by observation. This concreteness grounds the cosmic perspective, connecting vast abstractions to particular realities we can grasp and investigate. The next steps in that investigation are clear, even if the outcomes are not. Continue observing Proxima b with existing and upcoming instruments. refine models of its atmospheric chemistry and climate, search for signs of geological activity and magnetic field, develop biosignature detection strategies appropriate for the planet's particular conditions, integrate findings from Proxima b with findings from other exoplanet systems to build statistical understanding of habitability around M-dwarfs, pursue parallel investigations of potentially habitable bodies in our own solar system, maintain institutional and funding commitments necessary for long-term research programs, train the next generation of researchers who will carry the work forward. These steps are feasible with current and near-future capabilities. They require no breakthroughs, only sustained effort applying known methods. The breakthroughs, if they come, will emerge from this sustained effort, from the accumulated observations and refined models and tested hypotheses that systematic inquiry produces. Science advances not primarily through dramatic revelations, but through the patient accumulation of evidence and understanding. The study of Proxima b will advance the same way, incrementally but steadily, gradually resolving uncertainties and clarifying the picture. The picture that eventually emerges might show a sterile world, stripped of atmosphere by stellar activity, baked by radiation, geologically dead. Such a finding would disappoint hopes for nearby life, but would inform understanding of M-dwarf habitability throughout the galaxy. It would suggest that planets around red dwarfs face systematic challenges that most do not overcome, concentrating habitability around less common stellar types. The finding would be valuable even in its negativity, constraining models and guiding future searches toward more promising targets. Alternatively, the picture might show a world more complex than expected, an atmosphere maintained against stellar assault, signs of geological activity despite tidal locking, chemical disequilibria hinting at processes that might be biological. Such findings would demand explanation, generating new investigations, new models, new observations to test competing hypotheses. The finding would open inquiry rather than close it, raising the tantalizing possibility that life might exist in our cosmic neighborhood. Or the picture might remain ambiguous, with some observations suggesting habitability and others suggesting sterility, with data insufficient to resolve competing interpretations. Such ambiguity is common in frontier science, where measurements push instrumental limits and theories outrun evidence. The ambiguity would not be failure, but an accurate reflection of what the data permit. Resolution would require better instruments, more observations, longer time series, the accumulating effort that eventually converts ambiguity to clarity. Whatever the outcome, the investigation will have been worthwhile. The knowledge gained, whether positive or negative or ambiguous, advances understanding. The methods developed serve future investigations. The collaborations established persist beyond any single project. The inspiration generated ripples through culture. The cosmic perspective deepened and enriches human self-understanding. The study of Proxima b, regardless of what it ultimately reveals about life on that particular world, contributes to a larger project of understanding the universe and our place within it. And so, we arrive at the end of this exploration, not with dramatic revelation, but with calm acknowledgement of what we have learned and what remains to learn. Proxima b orbits silently 4 light-years away, indifferent to human curiosity, subject to physical processes that proceed regardless of our observation. We have peered at this world through our instruments, constructed models of its properties, assessed its potential for harboring life. We have found challenges more daunting than early hopes suggested, complexities exceeding simple habitability calculations, uncertainties that will take decades to resolve. Yet we have also found reasons for continued inquiry. The questions matter. The methods exist. The institutions persist. The commitment endures. Generation after generation, humanity extends its understanding outward, from the local to the cosmic, from the familiar to the strange, from the known to the unknown. Proxima b represents one frontier in this ongoing expansion, one world among many awaiting investigation, one set of questions among the countless questions that drive scientific curiosity. The dark truth about our nearest neighbor was indeed only the beginning. The beginning opened onto a vast landscape of inquiry, stretching from planetary physics to galactic evolution, from the chemistry of life to the philosophy of knowledge. We have traversed portions of this landscape, gaining perspective on its extent and complexity. Much remains unexplored, awaiting future investigators with future instruments and future insights. The night sky, visible from any place on Earth, contains Proxima Centauri among its countless points of light. Too faint to see without optical aid, yet present, real, accompanied by at least one planet and possibly more. That planet, Proxima b, circles its dim red star every 11 days, experiencing conditions we have only begun to understand. Whether life exists there, whether life could exist there, whether humans will ever know for certain, these questions remain open, inviting continued inquiry for as long as curiosity persists. The universe does not reveal its secrets easily. It demands patience, effort, ingenuity, and the willingness to accept provisional understanding while working toward deeper comprehension. The study of Proxima b embodies this demand, offering no quick answers, no easy conclusions, no dramatic resolutions. Only the slow accumulation of knowledge, the gradual refinement of understanding, the patient progress that characterizes science at its best. And perhaps that is the most important lesson of all. Not any particular fact about Proxima b, not any specific conclusion about habitability or life, but the reminder that understanding comes through sustained inquiry, that knowledge builds incrementally, that the deepest questions yield only to the most persistent investigation. The dark truth about our nearest neighbor taught us how much we did not know. The journey since has taught us how to know more. The journey ahead will teach us things we cannot yet imagine. For now, the investigation continues. Telescopes point toward Alpha Centauri. Spectrographs capture faint light from Proxima Centauri's wobble. Models run on computers, simulating atmospheres and climates and magnetic fields. Researchers analyze data, write papers, attend conferences, train students. The machinery of scientific inquiry operates steadily, producing the knowledge that future generations will inherit. Proxima b waits, as it has waited for billions of years, orbiting its ancient star, experiencing conditions we can only approximate from afar. If life exists there, it goes about its business unaware of distant observers wondering about its existence. If no life exists, the rocks and possible oceans and possible atmosphere continue their physical and chemical processes, indifferent to the questions asked about them. We wonder nonetheless. We ask questions, build instruments, make observations, construct models. We express through this inquiry something essential about human nature, the drive to understand that has characterized our species since its emergence. Proxima b receives our attention not because it asked for it, but because we cannot help giving it. The nearest potentially habitable world, beyond our solar system, compels investigation by its very existence. And so the story continues, not ending, but pausing, awaiting the observations and discoveries that will write its next chapters. The dark truth about Proxima b was only the beginning. What follows depends on what we do next, on the instruments we build, the observations we make, the insights we achieve. The universe offers infinite questions. Humanity offers persistent curiosity. The encounter between the two generates science, generates knowledge, generates the gradually deepening understanding that is our species' distinctive contribution to cosmic history. The night deepens. The stars wheel overhead. Among them, invisible to casual observation, but present and real, Proxima Centauri shines with its faint red light, warming whatever worlds orbit within its reach. 4 light-years away, yet closer than any other star, it represents both the vastness of interstellar distances and the possibility of eventual contact. The journey there will be long. The journey of understanding is already underway. Rest now, with the knowledge that the inquiry continues. The questions raised by Proxima b will find answers, in time, through the patient work of countless investigators. The dark truth was only the beginning. The beginning has led to deeper understanding, and deeper understanding will lead to deeper still. The cosmos awaits, patient and immense, ready to reveal its secrets to those who ask the right questions and possess the patience to await the answers. The story of Proxima b is the story of human curiosity confronting cosmic mystery. It is a story without end, because the questions regenerate faster than answers accumulate, because each discovery opens new territories for exploration, because the universe is far larger and stranger than any single investigation can encompass. We are privileged to live in an era when this story has begun in earnest, when instruments exist to probe nearby exoplanets, when the question of life beyond Earth has become scientifically tractable. What our era begins, future eras will continue. And that continuation is not a burden, but a gift. The questions are good questions. The pursuit of answers is good work. The knowledge gained benefits all. The cosmic perspective enriched by that knowledge improves human self-understanding and perhaps human behavior. The study of Proxima b, small as it might seem against the scale of the universe, contributes to something profound. The ongoing project of a conscious species seeking to understand the reality it inhabits. That project continues, tonight and every night, as telescopes open and observations accumulate, and understanding deepens. Proxima b remains 4 light-years away, but closer in understanding than it was before this exploration began. The dark truth was only the beginning. What comes next remains to be discovered. The stars shine on. The questions persist. The search continues. And somewhere, perhaps, life exists that we have not yet found, waiting for the moment when human curiosity and cosmic reality finally meet.